Hello. Hello and welcome to this video. In this video, we are going to talk about multithreading in general in C. This presentation contains some code, but the code is not right now important. So first question is, what is POSIX threads? POSIX threads is a user level library which maps the threads created by the library to kernel threads. Okay. So now C and C++ both have their own threading library. We don't need POSIX threads, but before, I believe C11 or C14, C11, I think. That is when C++ got thread. C got threads in C11. C++ got probably in C++11, I don't exactly remember. But when these languages got thread, the thread library mapped to P threads. Now they have their own implementation. I'm not sure if GCC implements threads for C or whether it maps to P threads, but C++ definitely has thread. But anyway, that is not something we are going to discuss this. So why we are going to discuss POSIX threads is because a lot of legacy code contain POSIX threads, and there is so much code written using POSIX threads that you just have to know POSIX threads. And once you know POSIX threads, you can go ahead and learn C++ thread library, and the concept will remain same. So first question which we have in multi-threading is, what is a thread? So if you have not yet done multi-threaded programming, then you would not have encountered threads. Threads are there in all the programs. Now, what is a thread? So most probably you have done single-threaded programming. That is, you write a main function that calls another function, that calls another function, and there is a path of execution. But in multi-threading, suppose you create one thread, then there are two paths of execution. One is that of the thread, another is that of the main thread. If you create two threads, then there are three paths of execution. Now these threads, the main thread and the threads which you create, may be scheduled in different CPUs. Most of the CPUs these days are multi-core. So these threads can get scheduled on different CPU cores. They may run in parallel or may not run in parallel. If you have a single core CPU, the threads may run concurrently. They will always run concurrently in single thread. So historically, why multi-threading was invented is that there used to be blocking IO. Okay. And when the main thread would block on IO, the program will suspend, and then the program can't do anything. So that's why the multi-threading was involved, so that the program can respond even if it is blocked on IO. The computation does not stop. One of the classic examples would be Emacs. So Emacs is single-threaded program, and is designed in such a way that multi-threading is very difficult. So for example, you open a remote file in tramp mode, then during the transfer of the file, your Emacs GUI cannot respond. So that is one of the classic things that what can happen in single-threaded program. So it might be difficult to imagine right now, but as we will go through code and look at the code, that's how it works, it will become more and more clear. In the beginning, getting your head wrapped around multi-threading is a bit difficult because it requires a different orientation of thinking. So why multi-threading is important is, I'll give you an example. Okay, MySQL has multiple threads, and when it receives a request for a query, one of the threads answers it. So if there is only one thread, then that thread will be busy doing computation for one connection. But if you have more than one thread, then multiple connections can be served in parallel. Same is the case with Apache server. There are threading models for web servers. So basically, multi-threading in general is there for concurrency and to some extent parallel computation. Okay. In general, it is for concurrency, but to some extent, it can do parallel computation if the program is designed in that way. So we will go through some of the terminology involved in multi-threading. So all threads in a process. So there can be multiple threads in a process. They share address space, that is heap, global and static variables, open file descriptors, process ID, signal handlers. While each thread has its own stack, register, program counter, and thread ID. Now the interesting thing is that each stack shares the thread. Now suppose we have by default 8 MB stack space in Linux, and we are spinning, let's say, 8 threads. That means the stack will be divided to 1 MB each. That is why it is important that if you are running heavily multi-thread program, then you should increase the stack space a bit so that the stack does not become too small for the thread. Now we compare processes and threads. Multiprocessing is also a way to achieve concurrency and parallelism. So processes have independent memory space, heavy to create, communicates via inter-process communication, and there is fault isolation. So if there is a problem, one process will crash, another will not. Then we have threads, we have shared memory space, lightweight to create, communication via shared memory, crashes, affect whole process. Now, if you look at the last item of the process, fault isolation, this is one of the reasons why modern browsers like Google Chrome or Firefox create a new process for every tab so that if something goes wrong, only one tab crashes and other tabs remain safe. Okay. Threads are efficient, but can be very nasty to debug. And if one thread crashes, then it will crash the whole process. They are lightweight to create, but coroutines are even lighter. We will study coroutines in C++ later on. So why use threads? Reasons are to use multi-core CPUs for true parallelism, overlap IO bound work with computation, as I said, improve responsiveness, example UI thread plus worker thread, cheaper context switches, and lower memory overhead than processors. So there can be an argument that whether we should have one process and multiple threads or multiple processes for the same thing. So there are different architectures related to that. One is using the locks, another using event loop, and one thread doing everything. Then we have thread per core architectures, and for very high concurrency requirement, thread per core architectures beat every other architecture. So in thread per core architecture, this does not happen. Communication between threads do not share locks or critical sections. We will see what happens in thread per core in a bit once we have gone through mutexes and all that. So as you saw that threads share heap global static variables, and when they modify the same variable, they take a lock around it, which is a mutex lock. Now, multiple threads, if they have contention on a lock, then the efficiency of the whole program goes down. And that is why thread per core architecture have been designed so that you do not take locks. There are no mutex locks in thread per core design, and threads communicate via inter-message passing, either through shared memory or through sockets or pipes or whatever mechanism you can imagine in inter-process communication. Threads can also make use of that. Now I don't want to get into C API of POSIX threads, but we will. You should not concern yourself with the code given in this particular presentation, because the reason is we will have plenty of time to study code. So let me talk more about architecture of threads. So one of the classic architectures is that suppose you have a shared variable and multiple threads want to modify it, then the typical way to do it is that threads take a lock on that. That is, only one thread is granted exclusive access to that particular piece of code where the variable is getting modified. And once a thread takes a lock, other threads cannot take a lock of that. Okay, they have to wait for the lock to be released. And that release can happen through something called condition variables. Okay, that is one thing. Then there are semaphores, which are counters which can be used to take the logs. So semaphores are different than mutex boxes, and we will come to that pretty much later. So the classic architecture is that you take a lock and you unlock and you work. Then we have something like Node.js where there is only one thread and it waits for events. That is, the socket is ready to be read, and when the socket is ready to be read, it reads the socket, it reads the data, what comes into that particular port to which the process is bound, and uploads it for computation. Okay, so that is your event loop. Now, there are concepts of worker threads, but Node.js worker threads are not like real worker threads. Okay, that is, they are not a POSIX thread separately. There is essentially only one thread. Node, because JavaScript in essence is a single thread programming language. Now, there are other mechanisms for achieving concurrency like Go routines. Okay, Go routines are somewhat similar to coroutines, but we will not go into go specific of Go routines, but we will talk about coroutines. Multiple coroutines you suspend on IO and resume when they have to do computation. So multiple coroutines can run within a single thread. A huge number of coroutines can be spawned because coroutines take very little memory, and they don't. There are two different types of coroutines. One is stackful, another is stackless. So we will also not go into depth of coroutines. Now the another architecture is thread per core systems. For example, C star is there, Glomio is there, Mono IO, and Comp IO is there. There are lots of thread per core services are there. So what they do is they have one main thread running in the event loop, and it reads the data and uploads it to other threads for work. And when other threads finish the work, then that response is given back to the client. Now these threads do not use mutexes to lock a piece of data or a variable. They instead pass the variable either by a reference or by address or by copying. It depends on how you are passing the variable. It is not really by address, it is mostly by copy. It is called message passing mechanism. So message passing can be done in many different ways. Okay, but we'll not go into that depth right now. So assume that there is a piece of data which needs to be modified by some other thread, you pass it, and that thread modifies that and sends back the result. And that's how you do the computation. So thread per core systems are very efficient, and they have very high concurrency. That is, they can satisfy a lot of work or clients at the same time. So that is the introduction to threads. And if you want to see some basics, then let's see. So to compile the program, you have to link with pthread, okay, minus pthread, or you basically you link with minus L pthread. That is the GCC syntax, not pthread. Okay. And pthreads are available on Linux, macOS, BSD, or other POSIX compliant systems. So how do you create a thread? You create a thread by calling pthread underscore create, and these are the arguments. We will not go into details of that. So for example, you see this pthread created by this say hello function. So this will run on an entire different thread. So it might run on the same CPU core, it might run on a different CPU core. We don't know that. That depends on the scheduler, how scheduler is going to schedule it. But this is the simplest pthread program. And then you have to waiting for threads, but we'll go into detail of exact thing probably in the next video. So I'll stop here, and I hope that you have got at least some basics of threads clear, how the architecture works. And if you have not understood everything, then I would recommend that you watch the video at least twice, so that you understand some of it. I know that when you are new, it is hard to understand without examples, and I have only talked theory in this video. So please wait for other videos to come where we will do real programming and we will have programs and we will see how threading works. Now, one of the downsides of threads is that there can be data race if you do not write the code properly. And the other downside is that it is very nasty to debug multi-threaded program, because when you debug, the scheduler does not work the way it works in a real program. So you might not catch errors easily. For example, deadlocks might not happen when you try to debug the program. So debugging multi-threaded programs have always been a nightmare. But there are some techniques which alleviates that, and we will study those techniques as how we can avoid or rather debug the difficult programs to debug in multi-threading. So with this, I will end this video here, and I'll see you in the next one where we will discuss the uh, practical side of it, that is the programming, how we can create threads, how we can take mutex boxes, how we can do multi-thread programming in general using signal conditional variables, read-write locks, and all those things you study in all the gory detail. So please wait for the next video where we will start the multi-threaded programming. So thanks a lot for watching the video. I hope that you have enjoyed this one. And once we are done with multi-threading, we will go back to our C++ playlist. So I'll see you in the next one. Till then, keep learning, stay curious, and most importantly, enjoy.